Introduction to TTT diagrams. Here is a time temperature transformation diagram, also known as a TTT diagram. Another name for this is also isothermal transformation diagram, or IT diagram. This particular one is for 1080 carbon steel. And this video is only to interpret this diagram, not necessarily how to use it in heat treating circumstances. If we look at the diagram itself, on the left-hand side is temperature scale in degrees Celsius, as well as degrees Fahrenheit. Along the bottom, where the x-axis, is time. And time is in logarithmic scale, and it's in seconds. These are all in seconds, and it goes into minutes, and then the hours, and the days and weeks in the logarithmic scale, in seconds. Below it is an end quench hardenability curve. This one here. This is the hardness, and there is martensite structure. This is also known as a Jominy end quench test. It's something that I wanted to show you for demonstration purposes. However, as you know, that hasn't been possible. Going back to our TTT diagram. This curve right here is known as the nose of the diagram. Nose of the diagram. This region up here, where it has the letter A, is austenite. These letters right here, they represent the phases in materials or steels, much like the phases in the equilibrium diagram. Austenite, ferrite, and cementite. That's what these letters represent. All the various phases: austenite, A, ferrite, cementite, also known as carbide, austenite, ferrite, cementite, and austenite, letter A. This first line right here, this says transformation begins. Austenite is unstable at room temperature. As the material cools, the austenite is going to transform to other structures. And this is where the transformation of austenite to other structures begins. And this is where all the transformation ends. What you have here then is the final microstructure. Down at the bottom is also martensite. So we have austenite, ferrite, cementite, and here is the microstructure called martensite, would form in this region. Remember, all phases are microstructures, but not all microstructures are phases. Look in here, this dotted line at about 425 Fahrenheit. Martensite starts. M sub S, little s represents a start, so martensite start at this temperature. 50% of the microstructure now has transformed to martensite, austenite transforming to martensite. And at this region, that represents 90% of the microstructure has transformed to martensite. That's at about 250 Fahrenheit, or about 125 Celsius. Going below that, you don't see any line here that says 100% transformation to martensite. That's because it doesn't occur until way below about minus 50 Celsius. Somewhere down here. This is the Celsius scale. So somewhere around minus 50 Celsius, minus 100 Celsius, all depending on the alloy, when you'll have 100% transformation of austenite to martensite. In effect, what will happen here at room temperature, where are we here? About room temperature, about 20 degrees Celsius, we'll get that the microstructure will be martensite, and there will be some retained austenite, all depending on the alloying elements, but there'll be some retained austenite in here. Having a look at this from another publication. Here it is here. It's a very good textbook that I like to use for physical metallurgy. Currently out of print. And within it is a chapter regarding isothermal transformation diagrams, otherwise known as IT diagrams. And here it is right here. Now let's look at this diagram as well. I'm going to try and zoom in a little bit See if I can, so we can see this a little clearer. At the top, we have stable austenite. And what this means is we have to go back to the equilibrium diagram. Here it is. This particular curve looks like it represents about 1080 steel. So let's look at the 1080. About here, 1080 steel. This diagram is good with respect to heat treating and getting materials from room temperature up to austenite. And we know here we need to go past A3 in order to get in the austenitic field. Once all the material is completely transformed to austenite and we do a quick cool or a quench, this diagram is no longer valid. This is only good for very slow cooling or very slow heating. We're interested in the cooling portion. So once we reach the austenite and we want to quench, this diagram here no longer is valid. So at that point, we begin here. That's where this diagram takes over, and it begins here where the austenite is at about 727 Celsius for 1080 steel. So to interpret this diagram, we start here when the material is already austenitic, 100% austenite. And then the material is quenched. During the quenching, a continuous cooling line or continuous cooling curve can be represented by my fan going down here with the temperatures inside of the materials cooling down at various different rates. I'll show you that in a few minutes. Looking back at this diagram, so we're starting with 100% austenite. So this region, this whole area right here to the left of this curve here that says martensite begins, or in transformation begins, transformation begins. That is all austenitic. Over here on the right hand side, after where it says transformation ends, various other microstructures then develop. Perlite, fine perlite, feathery bainite, and here it has acicular bainite. Here is the martensite start line, not much different than what I saw earlier, at about, and this is in degrees Celsius. So martensite starts at approximately, with this diagram, about 250 degrees Celsius, martensite start, M sub S. 50% martensite. Austenite then will have transformed to 50% martensite on a cooling curve that represents this kind of a line right here. Starting at austenite, and it cools quickly. It does not touch the nose of the curve. And martensite begins. Martensite start, 50% martensite, 90% martensite. Down here it says MF, that's martensite finish. You'll notice it's below 0 degrees Celsius. It's at about minus 50 Celsius. This martensite finish, depending on the alloy, will range somewhere minus 100, minus 75, somewhere in here, all depending on the alloying elements. At room temperature, after this quench is done and we anticipate 100% martensite, there's always a little bit of austenite left over because only 90% has been transformed. Again, this is highly dependent on the alloying elements. This is known as retained austenite. So we expect 100% martensite to be formed, and there's going to be a few grains left over of austenite known as retained austenite. Full transformation to martensite will only occur on minus 50, minus 75, minus 100. Going back to our other diagram. Start with austenite. Depending on the temperature curve, the cooling curve, the various microstructures that will occur, we're interested right now in doing a quench that, starting at austenite here, doing a quench so that the material cools down very quickly, passes the nose of the curve, and hits martensite. Austenite will then begin to transform to austenite, I should say, will begin to transform to martensite. Looking at some other diagrams, similar, I'm going to bring this back down a little bit. Let's have a look at this publication with regards to IT diagrams. This is from US Steel, printed in about 1963. Physics doesn't change. So all these IT diagrams are perfectly valid from the time they were made for that particular metal. Here's a similar curve. And this time all the various microstructures that one would see under a microscope are shown here. Again, we have the martensite start, 50%, and 90% range. You won't see complete martensite, typically. That is left for us to do. Looking inside, the nose of the curve is highly dependent on the carbon content. For 1008 steel, the nose of the curve here is virtually non-existent. As we go higher in carbon content, you notice the curve starts to develop. It's still non-existent. And if we go higher yet in carbon content, 1055 steel, this has some manganese added to it. You'll notice the curve here starts to develop. (1060), as we go higher in carbon, here is 1060 with manganese. Again, alloying elements have a tendency to push the nose of the curve to the right. Adding carbon will also push the nose of the curve to the right till eventually we get to the more common IT diagram, which is typically used for introduction purposes, the 1080. The eutectoid steel. So the greater the carbon content, the more the nose of the curve is pushed to the right, allowing us ability then to do a complete quench and form 100% martensite with a little bit of retained austenite. The next step after the IT diagrams is known as a CCT diagram, continuous cooling transformation curve. Allow me to show you that as soon as I get the book available. Here it is. And here is what a CCT diagram would look like. It's very much like the IT diagram, except most of it is always shifted over to the right. Here, this dark line, this C curve that you see here, this C shape, that is the actual CT diagram, continuous transformation diagram, or CCT diagram. These other lines here, these are cooling lines representing the temperatures within a metal which has been austenitized and then quenched. This cooling curve right here passes the nose of the curve, will go straight into martensite. Other cooling curves here do not go past the nose of the curve, and they go across the transformation begins and transformation end lines, and thus forming different microstructures here. This would be an annealing type curve. These cooling rates are best transposed on top of CCT diagrams. There's also various microstructures that are superimposed on these diagrams, much like this one. So I'm back to an IT diagram and the various microstructures superimposed on the IT diagram. And lastly, these IT diagrams can be used for cast irons. We didn't discuss cast irons. This is a course all unto itself, in my opinion. But here they are. Similar type of interpretation. A is austenite, C is cementite. Hope this video helps in interpreting IT diagrams.